Welcome, everybody. Good to see you all tuning in once again. I think this is our third pandemic meeting. I hope I'm right on that, because otherwise the days are just blowing together at this point. So we'll start off with the TNT forum. Roger, I think, has a pretty good presentation about slow scan TV for us. So Roger, if you're ready. Oh, and one last thing, if you saw Roger's email, hopefully you all kind of change the settings so you can hear his demo a little bit later on.
Okay, well, thank you, everyone. Today is April 10th, 2020, and we are sheltering in place at an undisclosed location somewhere in Northern Virginia. And it's already been mentioned, it'd be good if you could set the audio parameters correctly. Now, I'm going to give a very brief history of balloon operations at the Vienna Wireless Society. VWS has flown 8 high-altitude balloon flights. On one of them, an altitude of over 120,000 feet was achieved. And if you haven't seen Pete's K6BFA's video, there's a link and you can watch later. The payloads carried cameras with timers, but there was no live imagery. And when I got involved, we set up a mailing list and had some discussion. And there was very little interest in replicating the same mission with cameras with timers. But what was interesting was the idea that we might be able to have some sort of a live feed from a high altitude balloon at 100,000 feet if we're lucky, or higher. And the first thought was perhaps we could use a point of view system developed for drones. But these operate at 5.8 gigahertz. Professional drone operators will look at a thumbnail picture, and if they see something interesting, they'll remotely capture a high resolution image. But I did a free space propagation analysis, and if you put a 3 or 4 watt transmitter at 22 miles away, potentially, you would not receive an adequate signal on the ground. On the other hand, the same power for a 144 megahertz transmitter would be easily received on the ground. I wrote a memo about that, which I circulated, and anybody who wants a copy now can get in touch with me, but it's somewhat overtaken by events. So the next idea I had was, gee, we could perhaps create some sort of a live TV system, and I did know about slow scan TV on 100 and on 2 meters. I thought for about 30 seconds it was an original idea. Then I looked on the internet, discovered quite a few people have had high altitude balloon flights using 2 meter systems with slow scan TV. And there's a link at the bottom of this page to a particularly sophisticated system that a group in Europe put together. So I decided at that point, well, we haven't done it, but I didn't have any hands-on experience myself. So I figured I would build a sort of junk box slow scan TV prototype, run my experiments, and try to recruit some more volunteers in the club. A number of people have volunteered already. By junk box, I just mean I use mostly things at hand, and I haven't charged the club for any materials yet. We do have a budget this year. So what is slow scan TV? The formal name is narrowband television. The basic idea is pretty simple. You convert a single camera image to an audio file. Of course, the devil's in the details. How do you do that? Which I'm going to talk about. We're going to use what's called the Martin M1 protocol for a 320 by 256 pixel image. The time it takes to transmit a single frame is a function of the protocol and the image size. Then you transmit the audio file. It's something you could send by single sideband or by FM. If you are scanning across the band, you will hear it. And later on, when I play my video, you'll hear what it sounds like. Then the audio file, which might take 100 seconds to transmit, is received and rendered by the software line by line. And the strength is it's rather easy to implement. It doesn't require much bandwidth. 3 kilohertz for single sideband, 10 or 15 kilohertz for FM. And the disadvantages are it's rather slow, and it's just single frame transmission. There is amateur fast scan TV, but it's restricted to 70 centimeters and above and requires 6 megahertz of bandwidth, plus more elaborate equipment. Here are some examples of slow scan TV images. I like the one in the upper right. It was sent from the International Space Station, which has a 25-watt system on board, and the Russians occasionally, when they're manning the space station, send out slow scan images. This one is of a Yuri Gagarin stamp that someone received in 2015. Somewhat surprisingly, slow scan TV has been used for quite a few other purposes you wouldn't expect. The very first pictures from the moon of the Armstrong mission, Apollo 11, were actually sent using a slow scan TV system. And the table on the left is just for reference. There won't be a quiz afterwards, but it shows popular frequencies where people often use single sideband to transmit slow scan TV images in amateur radio. The protocol we're going to use is called the Martin Protocol, named after Martin Emerson, who worked for what was called the Robot Research Group and developed this. I never have gotten down into the raw code, but the abstract idea is that a given image is scanned, each raster line is scanned 3 times, once for green, once for blue, and once for red. The scans are sent as consecutive segments, separated by audio tones, and there's a raster line synchronization tone between each of these records. And simultaneously, the brightness at each point, the luminance, is encoded by modulating the audio frequency between 1500 hertz and 2300 hertz, which is also something you can hear if you have good hearing. Most people can hear, say, between 1000 hertz and 10,000 hertz, unless you reach the age you need hearing aids, where you may be cutting off at 2000. I want to give a shout out to someone I've never met, Jarrett Polder, because he implemented this algorithm in C code for Debian Linux, which I will explain. And he published the code on GitHub, and I downloaded it, compiled it, and ran it. And having this code already written by someone else made my life much simpler, made the project possible. Now I'm going to go over a quick system flowchart. These view graphs will all be online, so you can look at them later in detail if you wish. But the main program is running under Debian Linux on a Raspberry Pi Model 3B+, and I'll elaborate on that, augmented by many, many C libraries, which I didn't write. First of all, some of you may know what a Raspberry Pi computer is. A lot of you may not. What it is a series of microcomputers. The one that we're looking at, the one that I did my development on, is called the Model 3B+, and there's a picture of it right here, which I borrowed from another website. It has a lot of features: a micro USB port, an HDMI port, a camera serial interface, and an audio jack, which is necessary for the transmission we're going to be making. It also has an Ethernet port, a couple of USB ports, and what you can't see is it has Wi-Fi. And finally, 2 things are very important. On the upper side, you see this bank of pins. That's called the general purpose I/O breakout. They're vertical pins, and they permit you to set from within a C or Python program. You can select a pin and set it to either 0 volts or 3.3 volts. And that's what permits a Raspberry Pi to control things in the outside world. I'm going to explain exactly how it's done. There's 2 or 3 other things that are important. This is a family of Linux processors, but it has no hard drive. All the data is stored on an SD microcard. That's one reason these are so inexpensive, somewhere between $10 and $40 or $50 a piece. So the operating system is on a 16 gigabit SD microcard. And when you collect data from the camera, you store it on the microcard and you read it off of the microcard. There's a subset of Linux called Debian Linux, a subset of Ubuntu Linux, for those of you that are familiar with Linux, that is developed for the Raspberry Pi and easy to install. And it comes complete with all of the C compilers and C++ compilers that you might need. You do have to add a monitor and a keyboard, so it's not quite a free computer. But when you do that, you have a real bona fide Linux machine for not very much money. Now here is the code loop that's going to be running, whoops. Here's the code loop that's going to be running inside of it. And I wrote the mainline code with calls to a lot of different libraries. And at the beginning of the code loop, first of all, you have a camera, which is external to the Raspberry Pi. The Raspberry Pi code is running inside a Raspberry Pi, which is indicated schematically by this dashed line. You take a high-resolution picture, you save the image file to the SD card, and you check to make sure that file name hasn't been used. And if it has, you increment the number of the file. So it's picture 01, picture 02, and that way you can never lose a file. You can never overwrite an existing file. Periodically, at some period cycle duty cycle, which is yet to be decided, you rescale a high resolution image to a small image, 320 by 256 pixels. You insert a call sign in the small image, which satisfies the FCC requirement to regularly identify your station. You convert the image to an audio file using the code, which I've already alluded to, developed and posted on GitHub. Then my program sets a Gpio pin to 3.3 volts. That goes to an interface, and we electrically start the Baofeng transmitter transmitting. Then we play and transmit the audio track, and that voltage is sent to the microphone input of the Baofeng. After we've played the audio track, we terminate the push-to-talk signal. In other words, we turn off the transmitter. And I'm going to explain in a little bit of detail how that's done. The first thing I found was I needed a cable. So I bought a cheap Baofeng microphone and I castrated it, cut off the microphone, kept the cable. This is what a Baofeng pin looks like. It looks like a Kenwood pin also. It has two pins on it. From the outside in, this is called the tip, the ring, and the sleeve. When you push the talk button on a Baofeng, what you're doing electrically is connecting the sleeve of the 3.5 millimeter pin to the ground, which is the sleeve of the 2.5 millimeter pin. The pins, of course, are connected to pins on the chip, which is inside the Baofeng, but we don't really have to worry about that. And when you present an audio signal, when you talk into the microphone, that voltage is applied between the ring of the 3.5 pin and the ground of the 2.5 pin. Now, I'd rather think in terms of wires than pins, so I'm just going to be quick on this. Having taken the cable apart and done a little bit of tracing, I found the red wire goes to the 3.5 millimeter ring, the white wire goes to the 3.5 millimeter sleeve, and the black wire goes to the 3.5 millimeter sleeve. There's a green wire also, which goes to the tip of the 2.5 millimeter pin, but we don't use it here. I hope this has set the groundwork for the next diagram, which is probably the only complicated diagram remaining before I proceed to give a number of demonstrations. This is the interface. It was designed by multiple people. I found lots of schematics online, and there's two parts to it. And my diagram is kind of a cross between a picture and a schematic, because when I first wrote a straight schematic, I could understand it, but I didn't think anybody else could. This is a representation of the Gpio pin output from the Raspberry Pi. And I have my code set so it can set a pin, happens to be Gpio pin 18, but that doesn't matter. I can set that to 3.3 volts or 0. And then the Raspberry Pi has a ground pin also right here. These are connected to an opto isolator. When the voltage on the Gpio pin is set to 3.3 volts, this light emitting diode is forward biased, gives off light. The phototransistor inside the opto isolator receives those handy photons, and the resistance drops sharply. And that, in effect, connects the white wire to the black wire, therefore turning on the transmitter. It's the electrical equivalent of push to talk. You may ask why we need an optical isolator. There's a couple of reasons, but the main reason is this. The Baofeng has its ground, and the Raspberry Pi has a ground. And if you simply grounded the white wire to a common ground, you're in great danger of having a ground loop. So by using an opto-isolator, you completely separate electrically the Baofeng ground from the Raspberry Pi ground. The bottom half of the circuit is probably easy to understand. There's an audio jack, and the output from the audio jack goes to a one-to-one audio transformer. And the output from the audio transformer goes to, guess what? The red wire, which goes to 0.1, the ring on the upper pin, and the black wire, which goes to the sleeve on the lower pin. So you're presenting the audio input to the microphone of the Baofeng, and that will be transmitted as long as the push-to-talk signal has been applied and the transmitter is transmitting. One little finesse is this potentiometer set to 80 ohms. I was trying to figure out theoretically exactly how to forward bias the opto-isolator, and finally I thought that's too much trouble. So I turned the potentiometer to its maximum resistance, set the pin out from the Raspberry Pi to 3.3 volts, and then turned down the resistance until the diode was forward biased and the transmitter of the Baofeng went on. And then I turned the resistance back up a bit. So the 80 ohms is experimental rather than being a nice piece of theory. Let's see. Okay, this is a picture of the entire layout. I guess I don't need that. There's a camera right here, the Raspberry Pi camera, going to the Raspberry Pi board through a ribbon connector. This is a breakout board from the Raspberry Pi, GPIO, and it simply permits you to make wireless circuits, solderless circuits, which can be driven by signals from the GPIO. I made the interface I previously showed on this board. It kept falling apart, so I ported the interface to a small piece of permaboard and soldered things in place. I didn't have all the wire I needed, like 30 gauge, so it's not the best permaboard, but it works. And then the cable from the permaboard goes over to the Baofeng, which is set for 146.30 because there's no Virginia repeaters set to that frequency. Here's a picture of the receiving station on my deck. And on the left, I have my FT2900, and it's connected through a audio patch cable from the microphone output to a laptop, which is next to it, running a freeware piece of program which receives an SSTV audio track and renders the underlying image. And I'm going to demonstrate that. There's also a splitter going to a pair of speakers so you can actually hear what's going on. There are a lot of different cameras available for the Baofeng. I'm just showing two. These are two I own. The one on the left is an Argucam Fisheye Camera. It has 5 megapixels. The newer models have 8 megapixels, but 5 is fine for our experiments. And it has a field of view of 180 degrees. The camera on the right cost $8. It's a Raspberry Pi camera module, 5 megapixels. It has a field of view of 65 degrees. They both have a 1/4-inch aperture, and interestingly, they both use the same camera module, an OV5647. But the difference is in the lens. This has perfectly ordinary lens. This, you can see, is kind of a hemispherical lens, and the aperture is right in the center of it. The lens is fishbowl shaped, or maybe fish eye shaped, and much larger than the lens proper. Now here's a couple of pictures I took out in the backyard. And the one on the left was taken with a regular camera, 65-degree field of view, 800 by 800 pixels. There are two landmarks here. This is an oak tree, as well as being a significant part of my antenna setup. And within this square, you should be able to see my neighbor's house just over the fence. These are small lots, 1/3 of an acre. The picture on the right was taken from exactly the same location using the fisheye camera, 180-degree field of view. Here's the picture, here's the tree in the left, and here's the tree in the right. You can see the field of view. I can see it, though you may not be able to. Actually goes from one side of my yard to the other, which is pretty remarkable. This redwood-looking thing is the rail it's sitting on. My neighbor's house, which is about a 1-inch square here, has now been compressed and is in the back of the Raspberry Pi image taken with the fisheye camera. So the fisheye camera provides a much better field of view, but it does distort the image. And I would think that it would be much better to use a fisheye camera for a high altitude balloon launch, but I'm not sure. And, oh, good Lord. And here are the two images, which are compressed to 320 by 256 images, pixel images formatted for SSTV transmission. You can see they're smaller. You can see my call sign is in the upper left. And now I'm going to try to show a video. And I'm going to start it, and I hope you can hear the sound.
Hello everyone, this is Kilo Mike 4, Lima Hotel Z. It's April 5th, 2020, about 3 o'clock in the afternoon, and I'm standing in my upper deck, our upper deck, looking at the backyard, which is absolutely beautiful. And that's one reason I'm showing that to you. It's a good way to start a video. And a lot of things are in bloom, and it's lovely to be out here. But the other reason I'm showing it to you is because I'm going to attempt to demonstrate a slow scan TV transmission. I built a prototype of a slow scan TV system that might be enhanced and used for a high altitude balloon launch. And today I'm just trying to give a demonstration. So we're going to start by going over the pieces on the transmit side. In the upper left-hand corner, there's a Raspberry Pi camera. It's 5 megapixels. Nowadays, you can buy 8 megapixel cameras, which are more expensive. That's sufficient for our needs. There's a narrow ribbon coming from it, a narrow ribbon cable. And you can see the narrow ribbon cable goes to the Raspberry Pi Model 3B Plus in the center of the screen. You can also see there's an audio jack, which is part of the Raspberry Pi Model 3B Plus. Not all RPs have them. And that is connected to an audio patch cable, which will carry the slow scan TV signal when the image is scanned and converted to a sound file. Above the yellow jack, there's an HDMI cable which runs over to a monitor which is in back of me, and above that is the cord connected to the power supply. On the right, there's a broad ribbon cable, which underneath is connected to what's called the Raspberry Pi GPIO, General Purpose I/O. And it's just an array with a large number of pins that permit you to connect things to the Raspberry Pi and execute various actions when the program is running. The wide ribbon is actually connected to what's called a breakout board. The breakout board, you have the incoming cable, then you have that T-shaped device which has pins on the bottom, and the pins are seated in a solderless breadboard. And the breadboard, of course, can be used for prototyping. Coming out of that breadboard, I pick off two signals. The yellow signal is the Raspberry Pi ground, and the red signal is pin 18 on the GPIO, which will be used to start the push-to-talk protocol for the Baofeng. Both of these wires go to an interface board. I originally prototyped the entire interface on the solderless board, but it turned out to be quite fragile and difficult to adjust. So after I got it working, I put all the parts on that small perma board, which you see. And in the center of the perma board, you see a coiled cable coming down. That is a truncated Baofeng microphone cord, and the end of it is the double pin connector, which you're probably all familiar with, that plugs into the Baofeng, and that carries the signal to start push, and that carries the signal that causes the push-to-talk action to be taken, and it also carries the audio channel, which goes to the microphone input of the Baofeng. And finally, on the right, you see the two wires coming into the board, and those are the ground and the microphone signal for the audio respectively, for the sound file being played on the Raspberry Pi. So let's step back. Here is a Dell Monitor, which is hooked up to the whole apparatus by an HDMI cable. And it is just a monitor, it is not a workstation. Everything you will see on it is being executed on the Raspberry Pi by the Debian Linux operating system, running a large C code program that I wrote with calls to many, many C libraries that I did not write. Now, in order to actually demonstrate the intermediate steps, you notice I have my Vienna Wireless jacket hanging on the back of the chair. And the reason is there's a lot of glare today, and when I tried to photograph the screen, I couldn't do it. But if you take the Vienna Wireless jacket and throw it over the screen, you have a very nice hood, and you can see the screen, because the Vienna Wireless jacket is black and opaque. So it's not only a fine piece of apparel, but it's an excellent emergency sunscreen hood. Let's walk inside onto the covered part of the deck. It's nice to get out from the glare. On the receive side, all of 5 feet away, we have an FT2900, Yazoo FT2900, also set for 146/630. The coax connector for the antenna on the back is not connected to a coax. I just took a bare piece of wire and inserted it in the middle of the coax connector, and the bare piece of wire ends there. Might be a quarter of a wavelength long, but then the transmitter is only 5 feet away. On the back of the Yazoo, very inconveniently located, is a female jack for headphones. And I've run a splitter out of that jack that goes off to the right. And coming off the splitter, there are 2 female jacks. One jack is connected to a pair of Sony speakers, because when the slow scan TV signal comes in, it's just an audio signal. It's a very peculiar warbling sound, and you might enjoy hearing it. Plus, you've probably run across it when you're scanning the ham bands, if you've been at this for a while, and next time you'll recognize what the signal is. The remaining female jack goes to a Sound Blaster card interface. It's that little black box hanging down to the right and plugged into a USB port on the Dell laptop. Finally, if you look at the laptop itself, you see there's a program running, RX SSTV, that will automatically detect the slow scan TV signal coming in, and it will determine the correct protocol and switch to it. The correct protocol being Martin 1. The image we're sending is 320 pixels by 256 pixels, and it's will take about 1.5 minutes to transmit. So, having done that, let's go to the really awkward part of the demonstration, where I take my jacket, put it over the monitor, and stick my head under the jacket. But now you can actually see the screen. And let's see, I'm going to start by hitting a carriage return, which doesn't work. So I have to re-enter the command. Let's see, and try it again. That time it does work. And the program is running on the RP, and now what you're looking at is a 600 by 800 pixel of a picture of the backyard taken by the Raspberry Pi camera just a moment ago. So it's a real-time single-frame picture. I know there's a lot of glare, but this image is reproduced in the view graphs. Now if I X this image out, the next thing the program should do, oops, oh boy, sorry, there we go, no, we don't go, there we go. Now the program has produced a small image, the one we're actually going to send within our lifetime. It's 320 pixels wide by 256 pixels high. It has my call sign in the upper left-hand corner. Don't worry if this is out of focus, we'll watch it being received. And then finally, we X this picture out. And we walk again over to the receiving station, 5 feet away. And I'm just going to sit down and try to hold the iPad as steady as possible. This is a one-hand video operation. I'm just shooting with my iPad. But again, the image being transmitted was just taken less than a minute or two ago, reduced to a much smaller image than the original, embedded with the call sign, translated into a WAV file based on the Martin protocol, and is now being transmitted as an audio signal, which you can hear, as well as being received by the SlowScan TV program, SlowScan TV program. Well, that completes the transmission of the image, and everything worked as advertised. And with that, that terminates this video.
Okay, so I will kill the video, and let's see. I guess I have to resume share. X this out. Oops.
There you go. You're back to home.
Yes, I want to share the screen again and finish.
Okay.
Can you see that?
Yep. Yep. You're good.
Let me enlarge it
Yep.
and move from the current slide. And there's just 2 more slides.
Okay.
Well, that completes the demonstration of a prototype. Originally, I thought I would be showing this at the club and then offering to go out to various people's houses if they wanted to take a look at it and make some suggestions. To make a system which is flyable, we need to use lithium batteries. That's a minor point because regular batteries will die when it gets extremely cold. A major task, but not that major a task, is the Model 3B Plus uses about 3 times as much power as a Raspberry Pi Zero. And I might try migrating the code to a Raspberry Pi model that has fewer features but uses much less power. The fault tolerance on the code could be improved. If there's an exception thrown, there's a couple of ways we could recover, go to the top of the loop or force a reboot. I'm not sure which. I'm pretty sure the code is reasonably safe from a fork fault. We haven't verified the helium availability yet. Last time I talked to the supplier, it was available, but it's not inexpensive. Sort of a more dramatic task would be to replace the Baofeng HT. One could replace it just with a lesser model of Baofeng, but there are modules available that can be used to build 2-meter systems. And if someone is interested in trying to do so, they could talk to me and we have some funding for it. The module would produce less power than a Baofeng, but it would be much lighter. And then there's the question of what the best antenna would be for a Baofeng or a 2-meter transmitter module. Could be a turnstile, could be an end-fed, could be something simple. I'll take questions and comments. I do want to thank the people that have volunteered so far. Pete has volunteered to help plan the route of the balloon. Kirk has volunteered to help. Andrew volunteered to help with some Raspberry Pi issues. If anybody else is interested, we have a mailing list, which they can join. So that's pretty much what I have to say tonight.
Okay. So if we have any questions, if anybody has any questions, want to use the raise your hand feature on the little ... something more, we can call on you. I'll kind of start off. I know you're talking about using the Raspberry Pi Zero, Roger. Is that the one you want to move to? That's the one you said, I think.
I would use a modern version of it because, first of all, it has to have a camera plug.
Yeah.
Second, it does not have an audio jack, although you can buy audio hats for it.
Okay.
But based on the online stories analysis I've read, a 3B Plus requires about 6 amps when it's idling, and a Raspberry Pi Zero requires 2 amps when it's idling. And so by saving power, we could certainly reduce the size of the battery pack that's needed. But the trade-offs may be unacceptable because the earlier Pis have much slower processors than the current broadband in the 3B Plus. The Model 4 is out of the question. That's runs too hot and it's designed for a workstation. Sorry, I'm losing my voice. It's hay fever, nothing more serious than that.
I'm not sure if I can see anybody raising their hand. Leon, do you see anything?
I don't. I don't have anything on chat right now. Maybe, Roger, I'll just ask one quick question. How big a balloon will we need to launch this, given the helium availability question?
Well, the balloon payload cannot exceed 3.1 pounds. Otherwise, the FAA requirements become significantly more onerous. And ideally, we'd like to fly a balloon inflated with 300 cubic feet of helium. That's about 1,516 grams. And that should be sufficient to obtain a reasonable altitude. And from our local supplier, we would need to procure one 264 cubic foot cylinder and one 72 cubic foot cylinder of helium.
The package itself has to weigh less than 3.1 pounds, or a whole new set of requirements kicks in regarding you would have to have a reflector, you would have to have a remote release, and you would have to have a lot of other conditions satisfied. But something with under 3.1 pounds with a parachute that would lower the payload after the bursts, and we would attach a Bionics, I think it's Bionics, it's a micro track GPS unit to the line holding the balloon, and that would broadcast the GPS position on a different radio frequency than the 2-meter transmitter is set for.
Cool. Anybody else have any questions?
I do.
Go ahead.
This is Tom, W7SUA.
Mm-hmm.
The other thing I remember from the last flight, we launched it from a location that the winds took it towards Washington, D.C., and the club president got hauled into the FAA, and I thought they told us we had to have a release, command release no matter what for any
Really?
future flights.
Wow. I didn't hear that part of the story.
Interesting. Wow.
I wonder if a timer would suffice as a release. There are thermal timers that could burn through the wire without requiring a ground release.
Well, the problem was the winds went differently than we and the FAA thought, and so it arced over and landed near Andrews Air Force Base.
I see, in the restricted zone. Yeah,
Yes.
my son used to be a fixed base radio operator, and he was always talking about people squawking on the wrong frequency and getting hauled in. They take zone violations very seriously, restricted air zone violations, airspace violations.
Yeah, this is Steve Palmer. I have a question about the cameras. Are
Sure.
you limited in the using the Raspberry Pi cameras, or will the software read and accept like a USB webcam?
I don't know. The Pis have a CSI plug on them and I hadn't thought about using anything else. Some of the Raspberry Pis, including this one, have USB ports. Some of the earlier ones do not. I don't see why it wouldn't work, but it would also depend on the power that's required by the camera.
Okay, Roger, that was great. Thank you very much. I think we have a lot to look forward to, and maybe one last question. I presume you've kind of already said this, but just reiterate, I'm sure you're looking for volunteers who'd like to participate with us and with you on this. And how can they do that if they want to?
Right. Well, there is a mailing list with Jazik set up. If somebody sends me an email, you can sign up on the mailing list yourself by writing to the address, which I do not remember offhand.
So
Probably my email.
you think you could maybe send the email out on the general reflector?
Yeah.
You'd
And if
probably-
anybody sends I'll send out instructions on the general reflector so you can get on the email. I'm most concerned about the mandatory requirement to have a remote release. That's not something I anticipated. And it might be not be possible. Don't know.
We'll have to look into that a little bit more for sure.
Yeah. So thanks, Tom.
Alrighty. Well, thank you very much, Roger. That was excellent.
You're welcome.
To see what we're working towards. So